Good day. We continue our discussion on the belt drives. So, today's lecture is lecture number 32 and you see just a quick recapitulation what we have done in the last class. So, this is for the V belt drive and you know that the V belt specifications are as given over here. So, there are 4 type of sections mainly, also I told you that there is also an E section present. So, depending upon the kilowatt range one has to select the typical belt for the use. Next one that we just talked about, that the designation of V belt, how we consider this. So, what happens that if we have a belt length something like this, then we know that this is the inside length and this is the pitch length. So, by the formula etc. what we have learnt earlier, we can determine the pitch length, where by use of this chart we have to find out that inside length, and this inside length whatever has been computed should be chosen as a nearest that is available in the design data book. And as an example, if we have chosen an B section belt and if it is inside length was 1016 mm, then we designate the belt as B1016/40, where 40 is the equivalent length in inches. And these are the different values to modify the pitch length and the inside length, means the relationship between the pitch length and the inside length. Now, we have learned about this particular equation which gives us the relationship between the belt tensions, that is T1 minus AMV square by T2 minus AMV square e to the power mu alpha. Now, what happens that due to the belt shape which is having some sort of wedge, this is, if you plot, this is the wedge angle what we are referring to, then you will be having, as because this surface is also coming in contact with the pulley groove. So, we will expect an additional frictional force that is coming into picture during the for the V belt drives. So, thereby this equation is modified to an extent, that is e to the power mu alpha by sin theta by 2, where theta is the belt wedge. Now, as for this reason, you know, you are having some extra frictional grip. What happens that V belt transmissions are more compared to a flat belt. And another feature that is also very important for the V belt is that it actually it actually is capable of transmitting power, that is what I told you, and the slip in the speed belts are almost negligible. However, what happens that if you consider the efficiency, then one can say that the efficiency of the flat belts are as a matter of fact little more compared to what we call about the V belt, although V belt has a more transmission ratio and the transmission ratio is around 1:15, it can go up to that. However, another thing is that the flat belt drives do not have any limitations of the center distance theoretically, but we have discussed about what should be roughly a length, it cannot be infinite. Okay. However, in the V belt center distance limitations are there, it should not be too large. The reason is that V belt sections are thicker compared to what you are getting in the flat belt, thereby the weight per unit length of the belt is more. So, thereby it creates difficulty in the sense that is more centrifugal force and other things will come into picture. So, thereby the performance won't be that good, and the flattering will be also more. So one has to limit the center distances in case of V-belt drive. We will talk about that particular part little later on. Now, one of the important part in the design of the V-belt system is that what is the kilowatt rating of V-belts. This means that what is the capacity of the V-belt. We have seen the V-belt can be utilized or used for a range. However, for each individual belt, what should be the amount of kilowatt it can transmit? Just have a look at the this particular slide once again. Now, all this kilowatt rating of V-belts as shown over here are for alpha equals to 180 degree. So, based on that particular one, a typical chart is given like that. You are having a belt section. Suppose you are having a belt section A. In a similar manner, the chart will be available for belt section B, C, so on and so forth. Okay. So, if you are having this chart for belt section A, then you will find out that the kilowatt rating of the V-belts are also dependent on the pitch diameters. So, for different pitch diameters, say D1, D2, D3, etc., what will happen? That again the kilowatt rating is based on to the belt speeds, that is N1, N2, N3, N4. So, if you are having an A section belt having a pitch diameter of D1 for the pulley, then correspondingly if it is running at speed N1, then the kilowatt rating of this belt is kW1. Similarly, for N2 speed it will be kW2, so on and so forth. So, if it is D2 pitch diameter and for the given speed it should be some other value like that. Here now I just given it symbolically. All these values in this, if you consider this as a matrix, are actually specified in a design data book. So, from this type of chart one can find out that what is the kilowatt rating of a typical belt section which is dependent on pitch diameters and the belt speed. Now, just now you have seen this particular kilowatt rating chart. The next one is a chart for V-belt design factors. Means here we shall discuss about the different type of design factors that normally are utilized while the V-belt selections are being made. The first one is the service factor, which is designated as CSRV. So, the subscript SRV denotes a service. The service factor for the V-belt and the flat belt are identical. There is not much, there is no change, almost there is no change between the service factors what you will be utilizing for flat belt or for the V-belt. It is typically dependent on the type of drives, environment and number of hours of operation, etc., as we have discussed for the flat belt. Now, the kilowatt rating, what you see in this particular chart, that requires certain modifications. What is that particular modification? The modifications of kilowatt rating comes out to be in this following manner. First of all, the kilowatt rating modifications are dependent on a value which is called equivalent smaller pulley diameter. Okay. Now, what is this one? You have a speed ratio or the velocity ratio to what we have told earlier. So, depending upon that, what is happening, that you have to determine an equivalent smaller pulley diameter. Means smaller pulley diameter may be ds, but equivalent pulley diameter DE should be, as a matter of fact, CVSPD into ds. That is, a V stands for V bolt, and the speed, what is the speed ratio, depending on that this equivalent pulley diameter has to be computed. The reason for this one is that normally what happens that in a drive both the pulley diameters are not the same. As a matter of fact, if one diameter is smaller than the other one, then basically there is a decrease in severity of the flexing that occurs in the belt, thereby the equivalent diameter becomes something else. So that's the reason one has to find out the speed ratio factor to determine equivalent smaller pulley diameter. Next part you will see that all the smaller pulley diameter what we will be considering is not ds but it is DE. That means what I mean to say is that now onwards, once depending upon this particular speed ratio factor, that is this particular factor, what will happen? We will compute a equivalent smaller diameter. This equivalent diameter is always for the smaller pulley, and whatever the modifications we will be coming across is based on this particular diameter of the smaller pulley. So first step is that you find out the speed ratio, and then you find out the speed ratio factor from the given chart, and you determine the equivalent smaller pulley diameter. Then you know, just like the flat belt drive what we have seen earlier, the angle of wrap correction factor. If angle alpha is not equals to 180 degree, then what happens? That the transmission capacity will be reduced, and thereby how much it is reduced, we will be using a factor which is called CVW. V stands for V bolt and W stands for the angle of wrap. In a similar manner, we will be getting another factor that is called belt length correction factor, which is given as C subscript V into L, where V stands for the V section belt and L stands for the length. Now what is this particular belt length correction factor? Normally what is happening that for a typical belt section there is an optimum belt length for which the kilowatt rating etc. has been designated or has been given in the design data book. If the belt length is small, then what happens? A belt is stressed more number of times, thereby its life is reduced. At the same time, if the belt length is larger, so obviously the reverse will happen. So depending upon this situation, that how much the belt is flexing in a given time, a belt length correction factor is introduced in a design. So obviously if the belt length is larger than what is the optimum length for the typical section, then you expect an increase in the power rating, and if it is lesser than that, the reverse situation will occur. That means you will expect a reduction in the power rating of a belt. So once you find out the power rating of a belt, then you can find out that what is the correction factors that has to be incorporated are basically these two. Now just for a while I just go back to the earlier slide that is given as this way. Now here, while we consider the speech diameters, alright, when we consider these particular values of the pitch diameters, normally what we will be considering that this D1, D2, D3 etc. should be equivalent the smaller pulley diameters. Okay, I have just talked about the pitch diameters. So this pitch diameter what you have computed should be converted to what? Should be converted to the speed ratio factor to equivalent smaller pulley diameter, and based on that you have to find out the kilowatt rating of the belt. Of course the belt speed is also in question. Now once you find out this particular one, then you have to modify the factors by these two factors like CVW and CVL. So the basic selection criteria of the V weld stands as what it is being given over here. Suppose the transmission ratio of V weld drive is, as I told you, is within 1:15. First of all, depending on power transmission, a belt section is selected. That I discussed in the last class in details, that you should choose the value, you should choose a belt section where the typical power transmission is not to be falling on the extreme ends, somewhere in the middle. So that will be the best way to choose. Secondly, the belt speed should be around 25 meters per second. So this is a situation that normally the most optimum speed of a V-belt drive is somewhat around in the vicinity of 25 meters per second. The first of all, what you have to do, you know that the speed ratio, as I told you, to be computed, and then depending on driving shaft speed and the chosen belt speed, driving pulley diameter to be calculated and selected from available standard sizes. Driven pulley diameter is calculated with the help of speed ratio and selected from available standard size. This I suppose you understand. That means what is the idea? The idea is that you can understand the belt speed V will be something like pi dn by 60, where N stands for the RPM and the D stands for the corresponding pulley diameter. It could be smaller diameter, it could be larger diameter. So you assume a belt speed V. So we assume a belt speed V equals to 25 and we know the speed, so correspondingly this diameter is obtained. Suppose this is the diameter of the driving pulley, that is normally a smaller one, so we are having this ds. So we know the speed ratio, that is d large by ds. So what is the d large? Just one second, I write it. So we know that speed ratio d large by ds is something. Okay, so depending upon that, if you can find out ds, then you find out dl. So once you find out this ds and dl, then what you have to do, you have to consult the design charts to find out what are the standard sizes for the both situations. So you select the standard sizes of the pulley and again recalculate that whether your choice gives a speed ratio that actually is required for the design. So in this case you have to do little bit of iterations to find out a very near speed ratio as per your requirement. Now once you now we continue the selection of V-belt. Again what I was told, speed ratio is recalculated to I think you should complete the sentence. So is to speed ratio is recalculated to what? To suit your what? Your requirement. You are satisfied with this speed ratio, recalculated speed ratio. So if you are satisfied, then just come down to the next step. So what is the next step? That you have to select the center distance. What should be the center distance? As I told you, the limit of center distance roughly as a guideline can be given as the equation suggests, that center distance should be larger than this larger pulley diameter, and it should be within 3 times the sum of the large and the small pulley diameters. So this is one guideline. Within that one, you should try to find out the center distance. Another important thing is that space availability is of course a point one should keep in mind, but also you try to see that if the center distance matches quite near to the standard belt length or optimum the belt length for the typical pulley you have chosen, that is the typical belt section you have chosen, that is the best one. However, all the points I have just told, now you have to take care of all these things and choose a suitable center distance, keeping in the mind the points that has been discussed over here. The belt length, as we have seen earlier, is computed as the pitch length, and corresponding inside length is determined, and then the nearest standard length is selected from the design table. This part already you have discussed while giving the designation of a V belt, and then you calculate the angle of wrap. So you know the values of C, you know the value of DL, you know the value of DS, so you should not find any difficulty in computing the belt length. Okay. Now, so once you compute the angle of wrap, well, we go to the next part. As I told you, equivalent smaller pulley diameter is determined from the speed ratio factor, and that you have determined. For the equivalent smaller pulley diameter and the selected belt speed, kilowatt rating of the chosen belt section is noted from the design chart. This one also we have discussed right now, how to choose the kilowatt rating from the design chart. Then next comes the design power. Actually, your required power is this one, that is multiplied by a service factor to get the design power. So that means design power is almost on some increment of the design power should be taken into consideration depending upon the service factor, and these service factors are listed again, I am just to mention, in the design book in a nice manner. Then what you do, you just modify the kilowatt rating of the belt. What are the modification factors? The modification factors for the belt are like this: the angle of wrap correction factor, that is a CVW, that is what we have discussed earlier, and then what it comes, the belt length correction factor, this is the CVL and CVW. So these two factors once you have found out, then you have to see that this modified kilowatt rating of the belt becomes the kilowatt rating of the belt. To find out that kilowatt rating of the belt, what you have consulted, DE for the smaller pulley and speed N, that is a belt speed. So depending upon those two features, you have found out that kilowatt rating, and of course say the section, say A section or B section, whatever you may be choosing. So for a given section, given belt speed and given equivalent smaller pulley diameter, you found out the kilowatt rating of the belt. And that kilowatt rating of the belt is modified with respect to these two factors to get the modified kilowatt rating of the belt. So you have to transmit a design power, and each belt is actually giving you this much of kilowatt rating. So if we divide the design power with the kilowatt rating of the belt, then you get the number of belts. So once you get the number of belts, say n, then your final designation is n belts of, say, A section, n belts, A section with a given belt length in millimeter, and this one will be in inch. So this is your specification for the drive. Of course, there you have mentioned the center distance because that is required to put the machines on the base. So this is a very simple way how you just select a V-belt drive. So overall designing requires a selection of the typical belts. So with this we find that we have an idea that whether it is an V-belt drive or it is a flat belt drive, how we select the situations, how we select the particular belt section or the belt cross section in case of flat belt and belt section in case of V-belt, so that for a given center distance or for a selected center distance and for given speeds of the drive and the driven shafts, we can design the belt drive. Now I think the particular idea what we have gathered by last two lectures can be very well summed up through a small problem. So let us look at a problem which we will be trying to solve at this moment. This is the data for designing a belt drive for the following. Drive, you are using an AC motor whose speed is 1440 rpm and it is operating for 10 hours, over 10 hours. The equipment you are driving is a compressor which is running at 900 rpm and the power transmission is 20 kilowatt. So this is the raw data what you are having. Look here, we do not have any idea of the center distances because neither the space, nothing is given over here. So although this choice of center distance really in this particular case becoming quite arbitrary, however we can just have an initial center distance set or the final center distance set depending upon some rough guidelines what we are going to discuss right now. Now let us consider the problem, just one second. Let us consider the problem initial data. So we have the speed ratio. Okay, if we are having this particular speed ratio, by the way, let us solve this problem considering, say we consider a flat belt drive. Okay, now once we consider the flat belt drive, then certain situations, as I told you, are required to be looked upon. That is, one is the belt speed. So if we consider the belt speed, we know it could be around 20 meters per second, because we know roughly the value is become 15 to 25, so somewhere in between 20 meters per second. Let us choose this particular one. Now this speed ratio or the velocity ratio also you can talk about is coming out to be 1440 by 900, and that comes out to be exactly 1.6. Then we have to decide about the belt material, and we consider something like an leather welt, which are quite common in use also. Okay, so for these things we start our design. Now once we consider this particular fact, the first is that if we consider the belt speed to be 20 meters per second as the steps we have discussed, so 20 meters per second equals to pi ds 1440 by 60. Okay, so that gives a value of ds. Once again, as I am telling you every time, please have a check on this particular calculations what I am doing over here. Okay, so this comes out to be 265.3 mm. In the similar manner, you can find out the diameter of the larger pulley, and that comes out to be something around 424.5 mm. Now in this case, if we look for the standard sizes, then it comes out to be the ds equals to 280 mm and d large comes out to be something like that 450 mm. So this is from the data book, okay, design book, sorry, design data book, okay, design data book, we get these particular values. So what we do, we'll be recalculating, alright, we'll be recalculating this particular speed ratio. So if we recalculate the speed ratio, we find dl by ds, that equals to 450 by 280, that comes out to be something like 1.607, say 1.61. So you see that the choice of this particular speed ratio is quite okay, because we have started, our idea was to get 1.6 and we have found out that it is coming out to be 1.67. So the choice of these two pulley diameters are quite okay. So we find this idea, that means once we get on one part of the design, that means this is finalized, that ds something is coming out to be 280 mm. If I do not put any dimensions, then you understand these are all millimeter, then MPa, oh sorry, MPa and Newton is the force. Okay, so this comes out to be 450 mm. Now in this case, we set a center distance, just as I told you that the nothing I have spoken about the center distance. Let us choose the center distance to be around 1500 mm. Why? Normally you see that if the center distance is more or very near to it, okay, is equal or not very near to it, is 2 times the dl plus ds, it is a good choice. Okay, so if we consider the sum of these two and multiply by 2, I think a value of 1500 is quite okay. As a matter of fact, this decision of 1500 in actual practice is dependent very much on the space availability, and that's the reason you will be getting more guideline if you have some concept of the space availability. But let us, for the sake of this problem solving, we consider this to be around 1500 mm. So if we consider the center distance to be 1500 mm, then you can very easily find out what is the belt length. So what is a belt length? We consider this drive to be an open drive system. So if we are having the open drive system, then from the formula you can please refer to your notebook what we have chosen earlier. So you will be finding out that this value, with the help of this value of C, this value of ds and this value of dl, comes out to be around 4151 mm. Now you make this value something lesser by approximately 1%. So if you make it lesser by approximately 1%, then what will happen, that the initial belt tension will be taken care of. This is purely a somewhat an experience rule, 1%, 1.5%, like that. If you make a shorten the belt length, then automatically it takes care of the initial tension that is required in a belt drive. Well, your experience will show, and some guidelines in these regards are also sometimes given in the design data book. Here for this particular problem, let us assume it to be shortened by 1%. So if it is so, then final belt length for the open drive is it what we have chosen, comes something around 4110. There is an approximate value is 4110 mm. So belt length is 4110 mm. So what you do, you cut a belt length and you put it together, and here is the joint. So as I told you, you should take care of this joint. Sometimes clips are attached, sometimes some means it is cemented. So those manufacturing cares you have to take into account. So we get another important information from this, that the belt length L0 I am talking about is 4110 mm. So we concentrate to the other parameters. So once you have found out all these things, you know that very easily you can find out the beta. Please refer to the drawing what beta means, and this beta means to find out the how much overlapping or underlapping has taken place in the pulleys. Okay, the angle gives you an idea. I mean, we have so sine inverse d large minus ds by 2c, that is the formula you have used, and you find it is 3.25 degree. So what you get, alpha for the smaller pulley, that is actually where of the interest, comes out to be something like that. If you subtract this value, twice of this value from 180 degree, then you get the value as 100. This is 6.5, so 173.5 degree, and this is converted to radians as 3.028 radians. So this is the value of the alpha s. For the belt of the leather, you can take the coefficient of friction something around 0.4. So if you take the coefficient friction something around 0.4, then you can compute the value of e to the power mu alpha s, and that comes out to be your 3.358. Okay, so you can find out this particular value of e to the power mu alpha, and which is given by this particular value. Now you know that we have got that equation for this particular the design power. Now in this case the design power is expressed in this manner. Can I just erase this page? So we have got this value, please keep in mind. Okay, I think that we can also erase this portion to get a larger area. So what I am just trying to say that next we compute the P design. Design is a service factor. For the given operation, you can see the service factor as consulted from the data book comes out to be around 1.3 by my choice. Okay, some difference might be coming from designers to designers. It's not very specific. One has to use his own judgment also. So in this case 1.3 into your requirement is 20, so that comes out to be 26 kilowatt. So the equation for the stress comes out to be like this, that 26 into 10 to the power 3 kilowatt watt is BT. Please once again refer to that one, sigma dash minus what is that one, you have the rho v square, and that is e to the power mu alpha minus 1 by e to the power mu alpha into v. Now the question comes, this is the belt thickness and this is a belt thickness and belt width. This value of sigma dash, what is that sigma dash? Is actual value of sigma dash is sigma multiplied by the angle of RAF factor, and what was the other factor? This is particular the speed factors, if it is done at some other speed etc. So that was SPD. Okay, so just please have a look into this actual expression in the theory we have covered. Now here taking into account of all this angle of RAP etc., the value of sigma dash can be taken as something around 2. What? The unit is megapascal. So this is a very standard value for the leather belt, and I am choosing this ideas. Okay, so if we consider these values, then what you get? You get BT2 minus the rho for belt material is 10 to the power 3 kg per meter cube multiplied by 20 square 10 to the power 6 to bring it to proper unit, and this value comes out to be 0.072 and multiplied by this velocity 20. So this gives you the value of BT something around 1157.4 millimeter square. So if we choose a standard size of thickness to be around 6.5 mm, then it comes out to be, B comes out to be around 180 as a standard size. So this is the way you have chosen the belt, a leather belt of 6.5 mm thickness, and 180B is sufficient to consider your or to satisfy your design. Well, let us do one thing. The same problem, if we consider for a V-belt drive, then how it comes out to be. Let us solve the same problem if it is a V-belt drive. Okay, same data. So what we are doing, that we consider some of the factors to be common. Say we consider the C to be around, just to avoid, C is the center distance. This is mm, and what you get, the value of the service factor, or P design rather, you can consider to be same as 26 kilowatt. However, as because it is an V-belt drive, we choose an economic velocity. V is an optimum one to be 25 meters per second. So if we consider V to be 25 meters per second, you will be finding out that the smaller pulley diameter, this comes out to be around 331.5 mm, and DL to be coming out to be 530.5 mm. So you get two values, 530.5 mm. If I cancel the standard sizes, then one combination comes out to be around 315 by 530. Okay, another combination comes out to be around this combination comes out to be 355 and 560. If you consider this speed ratio, this comes out to be 1.68. If you consider this speed ratio, this comes out to be 1.58. Okay, so I think that it will be better that if we choose this particular situation which is very near to the given speed ratio. So once it is done, then we put the value of ds, and so ds comes out to be 355 and dl comes out to be what, 560. C, we have chosen the same thing. Now you can see this C value, what is we have chosen, is less than the 3 times the ds plus dl, so it is quite okay. So that's the reason I am just repeating the same value. So in this way also you can compute the beta with the same formula. It comes out to be 3.92. If you compute the alpha s, then this comes out to be 172.2 degrees. So this is this I'm sorry, this is alpha s, not ls. So alpha s comes out to be 172.2 degree. So with this values of center distance and beta, alpha, all etc., you find that the value of L computed as 443.6 mm. Reduce it by 56 mm from the standard chart what you have seen. So this comes out to be around 4387.6. Now in this case, as because the kilowatt rating is 20, the choice of the belt is very much a C section. So what is the belt designation? So we require a belt designation. This is, you understand, this I have just written, this is the inside length. Okay, this is the inside length. What is the standard? As per the design data book, comes out to be very near to this value. This comes out to be something like this, 4394. So our designation is C4394 oblique, corresponding inches is 173. So this is your belt length, and so you have to buy from a market a B belt of C section, and this is, but how many belts you are going to buy, that we will be just quickly finding out. So the number of belts what you are going to find out will be dependent on what? The kilowatt rating per belt. Now to find out the kilowatt rating, first of all you know that you have to find out what? You have to find out the equivalent diameter, and this equivalent diameter what has been computed as DE, that comes out to be 355, equivalent smaller pulley diameter, to be more precise 1.12. this is the factor. Okay, that also I have found out from the design data book, you can consult also. So 398 mm. So depending upon these sieve dia and the belt speed of, belt speed of 25 meters per second, we find that kilowatt rating comes out to be something as 12.1 kilowatt. Then depending upon the length, so length correction factor CVL, I think this is the one what we have given, CVL comes out to be 1.04. that means we have used a belt which is little larger than the optimum one. This one defines, and angle of wrap, this factor comes out to be 0.98 for a C section belt. Okay, so looking at this particular two values, then what we understand? We understand that the modified kilowatt, okay, modified comes out to be what, or corrected, whatever you can say, 12.1 multiplied by 1.04 multiplied by 0.98, all these factors taken together, and that comes out to be equals to 12.33 kilowatt. So number of belts what is required is coming out to be 26. That I told you is the same as we have decided of the service factor to be 1.3. So now coming to the point, 26 divided by the modified factor comes out equals to 2.1. so say approximately 2. So how many belts we require? So our final designation comes out to be in the form something like this: 2 belts C 2 belts of C 4394 oblique 173. This is your requirement. So you can see that the same problem we have done, one for taking the flat belt drive and another for taking the V belt drive. So I hope that these two problem what we have just solved will give you an ample idea to how to do for the design parts. So this way, and this ends our lecture on belt drives. Thank you. Good day. Today you can see that we will start our lecture 33, which defines the design of shafts. Now in this case, you know, the shafts are very common type of members which are used in very widely in any machine designs element, and this is a very important aspects of any engineering systems. If you see where you can see rotating wheels, etc. Now we now go for a formal definition of what we call as the shaft. So we can see we see the definition of shaft as it is a rotating member, and in general what happens that it has got a circular cross section